So, Professor R Ramanujan is a Ramanujan name itself is a synonymous of mathematics. So, I mean, there's no second thought about it that we have a great personality among us. And after a long innings at IMS Chennai, he is presently a professor at Ajim Premji University, Bangalore. He was involved in the National Curriculum Framework 2005 and also an executive committee member in Mathematics Teachers Association and also International Commission on Mathematics, Mathematical Instructions. A lot of things are there in his bio sketch, but I'll read a few. So he has taught graduate courses on theory of computation, logic, game theory, distributed algorithms. He's on the editorial board of various journals such as ACM Transactions on Computational Logic, Journal of Philosophical Logic, Knowledge, Rationality and Action. Very difficult to list his achievements, but he's a, I mean, his mathematical contributions are known to people, but apart from mathematical contributions, he has done tremendous work for spreading mathematics education in India, especially in Tamil Nadu. He's done a lot of work. So he has been a member of several syllabus committee set up by the Tamil Nadu government since 1996. And also he has been president of Mathematics Teachers Association of India and has spearheaded many of association's initiatives. For more than 35 years, he has been associated with the Tamil Nadu Science Forum, a voluntary group, and he has written more than 100 articles in Thulir, a monthly science magazine for children in Tamil Nadu, published by TNSF on a variety of themes. Especially in 2020, he was awarded for prestigious Indira Gandhi Prize for the popularization of science by INSA. So let's all welcome with a huge round of applause, Professor R. Ramanujam. Thank you.
Thank you, sir.
Thank you so much. Thank you. Thank you very much. Thank you, Vijay, for the introduction, long introduction. So, yeah. So today, I'm here to talk about a problem posing in the classroom. And let me start with thanking you, Sunil Bajaj and Johaki and the organizing team for giving me this opportunity. If you have any comments, questions for which we don't have time, my email address is here, very easy to remember. So please feel free to contact me anytime on any of these issues.
When you have jam in your thoughts, then you can call only jam.
Yeah, sure. Yeah. So let me start the quote by Paul Ramos, where he starts out with asking this question: what does mathematics really consist of? Axioms such as the parallel postulate, theorems such as the fundamental theorem of algebra, proofs such as Gödel's proof of undecidability, definitions such as the Menger definition of dimension, theories such as category theory, formulas such as Cauchy's integral formula, methods such as the method of successive approximations. Because mathematics, when you think of mathematics, you do think of many such things. Its techniques, methods, theorems, definitions, proofs. And then he goes on to add, mathematics could surely not exist without these ingredients. They are all essential. It's nevertheless a tenable point of view that none of them is in the heart of the subject, that the mathematician's main reason for existence is to solve problems, and that therefore what mathematics really consists of is problems and solutions. Okay, so this is I wanted to put this quote. So I teach this course called Nature and Methods of Mathematics at Haryana. And I usually ask students, do they agree with Hermos? I mean, this is one point of view. Of course, we are sure that is this what mathematics is about? And I think it's worth thinking about. I tend to agree with Hermos, that's why I'm standing here. But you may not. But it's okay. Then this is something to think about. And but really, problem solving, it's certainly true that even those who disagree with Hermos would still put problem solving somewhere at the center of mathematical activity. So what is all this fuss? What is all the fuss about? And what role does it have in our classrooms? If problem solving is all that important, how much problem solving do we do in our classrooms? And when I say our classrooms, I mean from primary school to PhD, grad school. Doesn't matter. So, so first thing I want to say is that problem solving is not equal to entire chapter itself. Right? Anytime you have text, you read mathematical text, you need to go do some problems. But those problems are every section will have some problems, every chapter will have some problems. That's you have to do those exercises. That's how you learn the text. I mean, yesterday Ashley gave this very nice talk on problem posing, and she was pointing out that what children, when she wants children to do problem posing, what they do is to take exercises in the book, but that's what we all do as teachers as well, right? Much of problem solving in the classroom tends to be there is a certain text that I teach you. I want to make sure you understood it, and I might make it interesting. Yeah, Gita, yeah, I think Satya also pointed out about the exercises they were doing, where it asked minute, like one group poses the thing, but this is still the exercises that instead of me doing the exercises, you are asking the students to do those exercises. Instead of the textbook providing the exercises, it's still end of chapter exercises, right? Typically, when Amos is talking about problem solving, and we talk about problem solving in mathematics, that's not what we have in mind. It's something more. I think you should understand what that is about. So I'll come to that. Yeah. So I think for me, the analogy is something like music, right? You, when you learn music, sa, pa, sa, sa, re, ga, you have to do and those are the inter-chapter exercises. You have to learn music, you have to learn the notes. Huh? You are made to do all that. But गाना गाते हैं ना, वो ऐसा नहीं है, right? So, I mean, for me, Ghana means Kishore Kumar, Mohammed Rafi. That you don't learn by notes and all. You just listen and कुछ तो करते हैं ना, you try. कुछ आनंद आता है ना, right? That is the joy that people are talking about in problem solving. Something you understand and you express. It may not be original, right? This is not like Ustad Amit Khan doing yesterday, right? That is not the thing we are talking about. What is there in Kishore Kumar's song here? All of us have heard it. All of us have heard it 1,000 times. Still, you want to go and sing, no? You want to sing it. You want to feel good. It's so we are not talking about problem composing. When I say problem posing, I am not talking about problem composing. Me sitting and creating a beautiful mathematical problem for you to solve. Don't think like that. Then we'll never get to it. We'll never be confident to do it also. Problem posing is like maybe I listen to 100 songs. Something that you like. We do a lot of problem solving. Some problems go into your head. But deciding which problem to pose in my classroom when is problem posing. Right? So that is when I say problem posing in the mathematics classroom, I'm talking about which Kishore Kumar song do I, gives me joy. And that joy I want to share with you. Right? Which Rafi song which I like so much and I want to share with you. Right? And choosing that song and actually doing it. Of course you screw it up. Yesterday, like बोल गया होता है यार क्या बात है होता है क्या बात है See, one thing that I keep telling in my teacher workshops, as mathematics teachers, school teachers, we do very important work. You know, जो काम कर रहे हैं it's very important work, it's critical work. But neurosurgeons थोड़ी हैं. We are not neurosurgeons. We have not cut up somebody's brain and something is going to happen. Nothing will go wrong. Nothing will go wrong if we don't make mistakes in the classroom. If we try problems that we cannot do, we screw up. No, parents will fall down. No problem. Right? It's not a big deal at all. One thing you may look foolish. Right? Like, oh yeah, then I come back, sit down and immediately all the lines come back. Happens to all of us. Big deal. So it's the spirit of problem solving is something like that. Trying it out, sticking your neck out, trying something. That's problem solving. So today when I'm talking about problem posing is entirely from the viewpoint of the teacher. I'm not talking about the kind of studies that Ashley was talking about, getting children to pose problems. That's very interesting as well. I don't want to go there. Today I'm only talking about the teacher posing problems in the classroom. And when I say posing problems, let me make it still clear. I'm not talking about composing. I'm not talking about us making a problem. It can be problems that we know. problems that we have done somewhere. It might have been inter-chapter exercise for me somewhere in something. It doesn't matter. In this context, you don't know it. For you, it's interesting. There is a pedagogical purpose. What is the problem that I use? But it should be genuine problem solving. It's not something that I taught something. Do you know the formula or not? That is, do you know the definition or not? Can you use the definition correctly? That is not what I'm talking about. This is fundamental difference. So, in it was just mentioned in the introduction that I've been part of this group called Tamil Science Forum. So there's a magazine called Tulil. It's the children's science magazine in Tamil, and it's a monthly magazine. I've been editor for it for a very long time. And one of the things that we did quite long ago now, nearly 27 years ago, I think, where we gave a call to mathematics teachers, science teachers also. It's a different story. Post interesting problems, right? And we get a prize and so on, all that. And something we got some 122 entries or something like that, out of which close to 100 were end of chapter exercises of some kind or the other. This guy is made interesting. Instead of asking directly, you match the following, you stand on your right, but it's basically something like that. So, and then we had several workshops. I've been part of Haryana in Tamil Nadu. We did some workshops on problem solving and problem solving with teachers. Sit with the unit, sit with some syllabus, say, take this part of algebra, take this part of geometry. What problems can we do? And then we did problem solving sessions. Can we do similar thing? And it was always very difficult. So what was going on? And then another thing that we were doing was doing workshops on open book assessments. And then somehow this seemed to be very challenging in mathematics. Right? Give open book exam, open book and open notes exam. This is for high school, secondary school, undergraduate classes, several workshops. These things kept coming up. If the book is in front of you, class notes is in front of you, what questions can you ask? And this is not something we as teachers, as a community, discuss very much. So there have been many such contexts where problem posing keeps popping up, as especially that I've seen over nearly 20 years now. And also had some sessions with high school students and also Olympiad problem sessions where many these things. And typically Olympiad problem sessions, children come up with some Russian problems. There are these Russian problem books. If you don't know them, I hope we'll talk about it. Shailesh here has written some lovely problem books. And these children who come for Olympiad sessions know about these things and they pose problem, very interesting things. And those are something different. Some of the things with high school students were great fun. Once in VS High School, I love going in Chennai, I had this very lovely session with, I think, class 11 students. When we broke them up into groups, and there was a December exam coming up. And the task given to the students was, okay, group one, design the question paper for the December exam as if Sangeeta were doing it. Group two, as if they all know their teachers very well. Your students know you very well. They know every mannerism of yours. In fact, ask the students what questions this teacher is going to ask. They do it. And I said, if you can predict all this, why are you doing bad in the exam? So students can even get into your mind and pose the questions that you would ask. Something is going on. Right? Why are we not using all of this for problem solving in classroom? Anyway, this is just an aside. My point is that problem solving as a culture in our classrooms, right, is something that what can we do about it? Like I have tried to maintain it as a discipline. You can ask my colleagues everywhere. Whatever classroom I go to, undergraduate classroom I go to, every class I always pose one problem. It may have nothing to do with the subject that I am teaching. It's simply a matter of mind discipline, right? So, and students know to expect this, that I will go write a problem before we start the class. And it's not for assessment. Some students try, some students come back, but it becomes part of everyday's expectation. So that's something that you do. If I believe that it's important, that's what I think I should do. But so what are good problems? So how do we pose such problems? And how do we pose problems to create a sustained interest? How do we pose problems with a pedagogic purpose? This is the sort of thing that I want to discuss today. And of course, very interesting is how do mathematicians pose interesting problems? Yeah, really, we have time to talk about it towards the end. So the point is that, once again, what do I mean by problem posing? Remember, it's Ghana and select. Right? It's a good listening to compare. You have a fund of Ghana, some songs in your head. Which song am I going to sing today? That's what. But there is a purpose here. There's a slightly different thing in the classroom. One purpose could be curiosity. Typically, you choose a puzzle. Right? So this is saying that next part. Yeah. So you choose some puzzle. Again, which puzzle do you choose? Right? You know how many puzzles. Which puzzle do I choose in my classroom today? Could be surprise, could be cleverness, showing off. Showing off is always good. Children love to show off, teachers love to show off, everybody loves to show off. Okay. Content, of course, for content. To look deeper into content knowledge, for conceptual and procedural fluency and skill. Polya talks so much about problem solving simply to develop yourself. And pedagogy, right? Of course, for pedagogy. To teach some strategies. There are certain kind of strategies that I want you to learn. Right? And certain big ideas. I'll talk about them as we go along. And certain kind of subtleties. I'll give examples of all these. And of course, what is very dear to me is exploration. Problem solving is wonderful because you can do open-ended problems. You can use them to make connections, especially algebra and geometry. I've heard Shailesh give beautiful talks on algebraic techniques for geometric problems and geometric techniques for algebraic problems. Those connections are extremely beautiful when you can do it. Critical thinking. You know, let's not forget that mathematics has a very, as a duty to teach critical thinking if you are looking at pedagogy in a democratic sense. So exploration can be wonderful in all these ways. So what are the characteristics of good problems? By definition, right? By definition, if you have purpose, if it achieves the purpose, it's a good problem. That's all. But there is one good symptom, right? There is a good test, litmus test of a good problem is that you solve it, it raises more questions, right? By the end of solving the problem, if you can think of two new questions, you answer the question, it leads to two new questions, it's a good problem. It should be basically capable of extensions and generalizations. These two words are very important in mathematics, extensions and generalizations. We'll see it further on that. Ideally, the process of solution should teach you new techniques. Right? That's really, the great problems are those. When you solve them, you learn a technique. Right? Not immediately by doing it several times. Of course, no technique. Technique never comes in one short thing. You have to repeat, you have to do many times without getting bored. That's very important. So here's a great one. This is again actually yesterday for those who listen was referring to Walter and Brown. There's a very nice book on problem posing by Marianne Brown has written a lot, and all her writings are classic in this regard. And here is one. Look at this. This is something that we all know. What is this? Some equation. X squared plus y squared equals z squared, one equation. So give me some solutions. Yeah, please give me some solutions. 3, 4, 5, okay.
6, 8, 10, y 12.
All Pythagorean intervals? Yes. Okay. What about I10? Yeah. That's a solution, no? Okay. Yeah. Go on. Go on, let me hear. What about root 2, root 3, root 5? Oh yeah, why cannot you give these solutions? Yeah. I can read that. How about, okay, I don't want you to give me solutions. Ask some questions around it. I've just put an equation. Ask me some questions. Stop.
What are the equations?
What are XYZ? Okay, huh? Are the solutions real? Okay. Are you looking for solutions on the real? Okay. Any other question? Okay. Does it have something to do with areas of triangles?
Would it be valid for other than a square?
Other than a square? Okay. Lovely. Okay.
Is this equation jumping group or complex number?
Yeah, I said I want more, so why not? Why real solutions? Why not complex solutions? Okay. Any more? Okay. We have some questions. How about some observations? Any okay. Something to do with squares?
Area of
Degree 2?
branch.
Degree 2? Orbits? Yes. Free variable? Somebody say free variable? Wow. Okay. And this is something new. Yeah. There are three free variables here. That's a good, very good logical point, right? There are three free variables here. Do you really mean for all x for all y for all z? Of course not here. You will exercise there is quite there, no? So these things are not free. They are essentially quantified in your head. Anyway, any other observation? Ah, it looks like some circle for us. Oh, yeah, yeah. Square plus y square equal to r square, you're supposed to write. Circle. Okay. Any other observation? Do this in class 9 with children. I've done this many times now. All kinds of questions. And sometimes nobody said anything about who did this, who did this equation, when children always ask, right? Somebody said Pythagoras, they're going to see by class 9 children know Pythagoras. So very one kid actually asked me, and this I've heard this twice so far in life. I treasure those moments. Say, what did people think before Pythagoras? Okay. And this was nothing. There is another child who once asked me, what did people think before Newton's laws? I thought it was a beautiful question. Right? Everybody, which is a rest or in a uniform state of motion, continues to do so until an external force is applied. Oh, great. People believe that suddenly you start going here. What did really Newton do? So, so the children ask all these kind of questions and observations. So, my point is, how do you use this as a point of departure to ask more questions, to raise more questions in the classroom? Yeah. Problem posing is something of this kind. Problem posing is this activity where you can take something that you know, perturb it, make it unfamiliar, render the familiar unfamiliar, and then you can start exploring. There's a lot that can happen. And here are some questions that Walter and Brown suggest. How about this? You said Pythagorean triples. What would integer solutions to x squared plus y squared equals z squared plus ಸ್ವಲ್ಪ adjust ಮಾಡಿ in Kannada we always say right? Plus minus 1. That's all I'm asking about. Okay. And here's something very, very nice. Okay. And if you actually start asking x cube plus y cube equals z cube plus minus 1, you're asking really some question that somebody knows that Ramanujan thought of. Right? And then x to the n plus y to the n equals z to the n for n greater than 3. Right? What does that remind you of? X to the n plus y to the n, it is x to the n plus y to the n equals z to the n. Looking for the initial solution n greater than 3. But what about plus minus 1? Ramanujan is a beautiful solution. Okay. So these are extremely interesting questions. Take the familiar, change it a little. So this, and Maria Brown takes it to a technology. To read her papers simply for the pleasure of where all she can go with this strategy. I warn you that I would say that I say it in appreciation of Maria Brown, but I also warn you it can lead to very difficult questions. But the point is, that this is the spirit of explanation that I'm explaining to you. So what she says is, do not accept the given. Somebody, just because somebody writes an equation x squared plus y squared equal to z squared, don't accept the given. Fight it. Fight it is polynomial. What about for what integer triples q of x squared plus y squared less than z squared? This is refusing to be limited by the given. How about thinking about inequality? Inequalities are difficult. Inequalities are a little bit dangerous, right? So for those who do linear programming, right? So solving linear equations is one thing. Doing linear inequalities is something else. It's more fun, but it teaches you a lot more. How about, okay, this is something to do with triangles, right? It's very clear. So Pythagoras theorem, you're thinking of rectangle, triangle. Yeah, that's what you're thinking of. What about quadrilaterals? Is there some equation like this? So that's a geometric reading of the equation rather than algebraic. Is there a three-dimensional law? Okay. See, the moment then, if I can think of x cube plus y cube equals z cube, I'd be thinking of some three-dimensional geometric figure. Volume. Is there a possibility? So this is basically a different reading of the exponent. After all, you said degree 2. So why not think of the other thing is that she says, I should say they because I'm referring to some of the earlier papers. Yeah. So simply list a few Pythagorean triples. You are said certain. Write it down on a piece of paper. Quickly write down you will see many. And when I say 3, 4, 5, I am including 6, 8, 10. Is it clear? Because you can always take multiples of that. So primitive, they call it primitive Pythagorean triples. But just write a few. Okay, I don't have the time for this. Usually we go to the board, write down a lot, and children or teachers are going and will start making observations. You know what all kind of observations you can make? And you typically write it in a canonical form, x less than y less than z. So that it's easy to learn. So you just do a table of x, y, z after you do it. You find that between x and y, one is odd and the other is even. Z is y plus 1, if x is odd, else z equals y plus 2. Children have come up with all these. All z's into your form for n plus 1. Every triple has one element divisible by 4 and one by 5. If z equals y plus 1, then y plus z equals x squared. If x is even, y plus z is actually x squared by 2. Whole lot of such stuff. So how much of it is incidental to the first few Pythagorean triples? How many of them are theorems? A lovely investigation actually. What about here? I'm offering a different problem. Yeah. Given two equilateral triangles, I give you two equilateral triangles A and B. And I'm asking you, find a third equilateral triangle C, whose area is the sum of the other two areas. How do you do it? Let's say that you don't need even a board for this. First rectangle triangle, call it side A. What is its area? Root 3 by 4 A squared. Okay. What is the second one? Root 3 by 4 B squared. What is the sum of the areas? Root 3 by 4 times A squared plus B squared. What is the C I'm looking for? So something area is root 3 by 4 C squared. So what is the equation I want? Okay, Anna? Okay, Anna? So what are we saying? What is the geometric interpretation of the equation now? I have a rectangle triangle, but I am not constructing squares on the side. I am constructing equilateral triangles on the side. And of course, the areas come out to be the same. Is this a different? It looks like a different problem. It's actually the same damn problem. You are looking at it instead of looking at squares. Because I said equilateral triangles, the same thing goes. This is problem posing with a pedagogic purpose. When I said, right, okay, I'm teaching, no problem. But I'm expanding the horizon in some fashion, right? And I'm not doing anything original. I'm not doing some badaya, right? I'm just singing a Kishore Kumar song, right? Remember, that's all I'm doing. Because this is the point clear? I hope my point is clear. So construct the third one. Yeah, you see it. Okay, then now we say that hi, this seems to work for squares. This seems to work for equilateral triangles. Can you find some other? So I take a rectangle triangle. Can I think of some other geometric figure that I can draw and still this equation holds?
Semicircle.
Yeah, come on. It is so perfectly timed. You had a big hand. You should say huge amount. Yeah. So semicircle, clearly pi r squared by 4. You'll see a squared plus b squared equals 6. The moment you start thinking like this, I assure you, start looking around, lots of a squared plus b squared equals 6 squared will be. Right? And that's wonderful learn. Right? This is really wonderful learn. And how about something with parallelograms? How about right angle triangles on top of right angle triangles? And go on constructing right angle triangles on these, you'll get lumpy figures. GeoGebra is good enough. Okay. Just start doing it, sit with 1 afternoon of GeoGebra, and you got like a wealth of stuff. Now comes the question, can we characterize this? So some similarity of figures is needed, because this is all we are writing areas. Right? So some similarity of figures is needed. Can we characterize similar figures for which the theorem holds? Now the exploration really, gets going. Okay. So this is all Paisa-Vasool from Pythagoras. That equation, I guess, that's all. So in some sense, this is the spirit of problem posing. And so what about, I also say problem posing for the big ideas. Like there are some big ideas of mathematics that make mathematics very powerful. Symmetry is one of the really beautiful ideas, right? One problem that I like very much is tic-tac-toe. Do you know what tic-tac-toe is? Yeah. Everybody plays 3 by 3. I put X, you put O. Right? Anybody who gets 3 in a row or 3 in a column or 3 along a diagonal wins. Yeah. I hope you know the game. I hope you play the game. Your children certainly do. It's a game to be played in class. And here is the problem. Count the number of filled in tic-tac-toe boards. When does the tic-tac-toe game stop? When somebody has got 3 in a row or one. That means I have, let's say, X wins. I have put 3 X's. But it's turn-based, right? The moment I put an X, you must have put an O. Then only I can be back next. So when the tic-tac-toe is filled in, you should have at least 5 entries. Right? Maybe 3 X and 2 O's. That is the minimum. Right? So now you can ask, count the number of filled in tic-tac-toe boards. Try to do it. There are lots of possibilities. You can have X's all here, X here, this thing, you can start counting. And this is at some point you start using and choose and so on, and you actually figure it out. This is like, I would say half an hour to 45 minutes. You can sit and do it. It's a good exercise. But that's not my interest. Okay, you can actually come up with a number. Tic-tac-toe, this 5 is already, or you can think of 5 X's and 4 O's. Simply count them, right? What are the different ways? You can have 5 X's and 4 O's. Count the number of tic-tac-toe boards. That is a very nice answer. But that's not my goal. But now, if I take a filled in tic-tac-toe board, I rotate it. Rotate it by 90 degrees. Will it still continue to be solution position? Rotate it by 180 degrees. Rotate it by 270. If I flip it like this. So if I rotate it and reflect it, now this is something you should just do with it. Right? Get them to do. Draw them. Children have no problem because it comes from a game. Right? You ask them to draw it, ask them to redo it, and maybe there is a nice tech tool to do these things. I don't know all of them. I have only done right? So, and you can do a lot. And then you realize that many tic-tac-toe boards remain the same. Right? Some of them change, but they're still solutions. Okay. That's very nice. So you make a lot of observations. So the technology all along is always this. You look at something, you ask questions, you make observations, you do something, make more observations, ask more questions. That's all you are doing. What do you find? Now comes the thing. Okay, there are some boards that you will hit. No matter what you do, remains identical. How many are there? How many are those boards? Just have terminology that are rigid under rotations and reflections. And with tic-tac-toe, it's small enough, you will actually find them. I guarantee you, will find them. So now you can actually talk about the orbits of a board. And again, these things I'm telling you, I have been doing class 9, class 11 children. 10 and 12 are usually abandoned us. We are never given an opportunity to work with them. But of course, I'm only talking about it at a math club more. In teacher workshop, just last month, there was a teacher workshop in Raichur where we were sitting and doing these orbits of different boards. So this is something that you can happily do. You need time for each of these things, right? This is like one session, 2 sessions. This you can do. But what do I mean by orbits? What do I mean by orbit? So if I take a board, rotate it, I keep getting new board, right? Eventually it will come back. So that's one orbit. So you can look at all tic-tac-toe boards with 4 orbits, 8 orbits, and so on, and you can calculate. Finally, you get a number that's very pleasingly you've now seen. You started with, you counted the number of tic-tac-toe boards. Now you know that with these few of them, you can generate all the tic-tac-toe. Another one to do similar thing is 4x4 Sudoku. 5x9 Sudoku is very difficult. 4x4 Sudoku is wonderful. Sudoku, if you play the game, you know the constraints, right? Rows, there should be no repetition. Columns, there should be no repetition. Within boxes, there should be no repetition. 4x4 is very small. You can actually count the number of filled-in Sudoku boards, filled-in Sudoku grids. Here, I can even tell you the number. I don't think it is spoiled very fast. It's 255. And when you figure it out, why is it 255? That argument is very nice. Start looking at symmetries, looking at rotations. Sudoku has a lot more symmetry because of reflections. You can take 3 by, in this case, a band of size 2, 2 rows. 2 rows you can flip for another 2 rows. It will remain in solution. So a lot more actions that you can do. And then you will calculate. And what is very beautiful is at the end of which you get 3 Sudoku boards. 3 Sudoku grids from which you can generate all this. That's a wonderful level. And I love that, and I still love this thing when one kid asked me, okay, how did you know? Can you calculate this number? I'm waiting for it. It's called the Burnside lemma. Right? Wait, you will learn algebra, you will get to Burnside's lemma, and then you will know how to get this number. I knew this number because I knew Burnside's lemma. I could actually do it. This is the power that algebra is going to give you. Right? Okay, but point is, symmetry is a big idea of math. Employing symmetry, using symmetry is such a profound mathematical understanding, and that's accessible. You don't need to wait till group theory and you don't need to wait till all of this. You can give a taste of such problem solving. But here, this is guided. It's a problem posed. And of course, when I pose the problem, I have thought about the solution also. But this is not end of chapter exercise anywhere. Right? Here is something where what is the mathematics being employed? Children, this is mathematical thinking. This is not some particular curricular content that we are talking about. Another big idea is invariance. Rana was there last month and last month I was presenting in the lab conferences. And this is something that we've been doing. Now, another central and a very powerful mathematical idea is to change things like these rotations, etc. Asking what is invariant. What doesn't change? When I change something, what doesn't change is what we call invariance. And that's a powerful mathematical idea. Here is a very simple problem. This is with not even middle school, primary school children. You can do invariance. Right? This is class 5. We were doing this with class 5 children. Write numbers 1 to 20 on the board. Call 1. Pick any 2 numbers, erase them and try to sum. Instead of 20 numbers, we have 19 numbers now. Another child comes, pick two numbers, erase them, write the sum. You have to keep on doing it. What will happen in the end? You will be left with one number. The question now, when you start, is it odd or even? Now, with math five children, it's a lot of fun. They're desperately trying to strategize. So before you start, you say, how many things is odd? How many things is even? Some vote. Okay, odd by aggregate. So between you should keep trying, and in the end, what you get odd number? Then you have to take even again. Right? It's a lot of fun in game. Now you want them to predict. Is it always going to be odd? And of course, after they start doing it with the small children, there's no problem now. They're not getting bored when they're playing the game. Answer is always the same. What is going on? Right? Okay, and here starts a discussion. This discussion can be taken at different levels. For middle school, you do it at a different level. It's the same problem, right? But it's not for finding the right invention. I'm not going to give you the answer. I will. The next one is a little more difficult. With middle school children, we actually my colleague Jayashree, who's an IT Bharat now, we have done this many times, all kinds of invariants will be good. Yeah. But this is one. So this is instead of so you keep two numbers, don't put the sum, but put their difference. That is, take the bigger one, the smaller one. Subtract the smaller one from the bigger one. Right? So it's going to be smaller numbers going in, which may already be there. That means you don't have to write it. It will go down fast. Is it going to be odd or even? Again, I'm not going to give you the answer. Now, instead of this, now I can change the rules of the game with many things. There are like so many circles and so many triangles. If you pick two, put them in a box, cut them out. I pick two. If they are the same shape, put a different one. No, I can change the rules in many ways. Finally, only one will remain. You have to change whether it be a circular triangle. I put some 10 balls and 5 red balls. I give you pick two. They are the same color. They put this back. They're in different color. Put something. Put and I assure you, 100 variations are there. You can have a lot of fun, and children can play the game, do the reasoning, end with the proof. But in this process, whether whatever is going on, what you are teaching is a very important mathematical idea, and that is the invariance. Right? Come to a linear algebra class, you should introduce subspaces. You talk about span. You talk about linear mass. Right? You talk about linear transformations. You should talk about, okay, what are the things that leave my subspaces invariant? Right? Invariant subspace. You don't have to wait for the invariant subspace problem. Right? That's a grand problem. But the taste of invariance, if you don't see invariance, linear transformations to me are not as much. I'm saying these ideas extend from primary school to graduate school. Doesn't matter. There is a taste of symmetry. There is a taste of invariance. Right? Taste of limits. These are beautiful ideas of mathematics that we want to do. Here's the problem I'm going to pose again. This thing is best done with GeoGebra or something like that. Okay. Take the parabola, y equal to x squared. Okay. And I intersect it by a straight line. How does the straight line look? Like this, like this, like this. Choose whatever line. Basically, here. Now I move the line upwards or downwards with the slope remaining unchanged. And then you observe that the midpoint, so it cuts the parabola at two places, right? Look at the midpoint. That midpoint seems to move along a vertical line. Proof. Is it just an optical illusion that you are seeing? Right? So now this I just put there. I mean, you have people like Rana and Durrani sitting here. They give you hundreds and hundreds of such problems. I'm very sure. No problem. You just sit there, you will watch lots of action. I've seen Rana do something with quadrilaterals there. He shorts something here, something here, something here, something, and he said, no, that point doesn't change. Right? I've seen him do it in one word. So there are lots of such invariants you can see. This is lucky for me because those are invariants that you can see. Prove it. Right? And of course, GeoGebra is still the tools also. Some of the problem with GeoGebra, they don't need it because I want to ask questions with areas and adapting this with the area. I don't want to, I want to, discover it. So I don't know how to hide some part of GeoGebra and do. Yes. Some things we need to do. But the point is that there are invariants waiting all around. Typically, we think of it in geometric terms. That's why I didn't take geometric examples, like a combinatorial or this functions example. Where we forget that invariants are as important. Okay. How about problem posing for something very routine, symbol pushing? I mean, handling expressions is, I find one of the most important things in secondary school. We talked about secondary school algebra syllabus available in this discussion. I think we let down our children if we don't give them. On the other hand, we make it too boring. How is it possible to get children to develop comfort and facility with handling algebraic expressions of various kinds? No meaning. Think of it as expression. At that point, I'm not sure how much algebra you can do if you have to start attaching meaning to everything. Like function interpretation and all that, I know all that, is all goes so far. Right? You have to complicated stuff with, pushing things all around. You must develop a comfort with that. And if children don't get it in class 9 and 10, you're going to have a problem in higher secondary. Undergraduate mathematics is simply you can't do it. Right? So, how do we do that? Now, here is a very simple problem that we pose. Right? What is the diagram? Lots of blanks, right? 6x on the left hand side and I put square on the right hand side. Or there are two terms. From that, you can already guess that okay, some 6 has factors 2 and 3. 2 which कर सकते हैं, right? Yeah. Okay, something like, what is it that I can do? So we can start thinking like this, right? So create expressions, handle expressions, don't only solve, right? Okay. Now, there are like hundreds of exercises. This is still end of chapter exercises, but I'm just saying that little better can be done when we start thinking about it. Here, for instance, I give you 1 by 1 plus 1 by x, and x squared plus x by x squared plus y by x plus 1. They simplify to the same algebraic expression. Give at least 2 other algebraic expressions that simplify to the same. I'm not asking you to just simplify. I'm not asking you to see that these are the same. These are the same. But now do more. Right? So in the process, you might be able to think more, but this is nothing. Here's something that I think I already discussed with Shailesh. I love this problem because if I look at something like x squared minus 1 by x squared plus 1 equals x plus 1, and I ask you to think about how many solutions does it have. Yeah, this is horrible. I mean, x squared plus 1 is sitting in the bottom. If I transfer it to the other side, I get x squared plus 1 whole square. Fourth degree polynomial. Come on, guys. I mean, you don't want to start mess around with something like 1/4 degree and 1/2 degree. You push it, you can do all that, bring it to a form. You hope to solve it. I do. On the other hand, I can start looking at it and thinking about it, which is what I want. Okay. On top, I've got something of the form x squared minus 1. So I'm taking some positive quantity and I'm taking away 1. In the denominator, I'm taking a positive quantity and I'm adding 1. Can this fraction on the left hand side, can it be greater than 1? I'm sorry, can it be less than 1? Of course it's less than 1. Right? The numerator is smaller than the denominator because I have taken squares. I'm talking about positive quantity. So it's definitely going to be less than 1. On the right hand side, I've got x squared plus 1. So it's going to be always greater than 1. So this equation cannot have any solutions. That's it. Right? If you start, so handling expressions is not manipulating. This is symbol pushing. This is definitely symbol pushing. Mathematicians pejoratively call it symbol pushing. I really feel bad about it when I'm a computer science guy. I think symbol pushing is not easy. Symbol pushing should be taken seriously, respected, and dealt with appropriately. Right? I think this is good symbol pushing. Right? You're not doing any deep thing, but you're just looking at what you're doing a little carefully. That's all. And if you start thinking like this, algebra is a fundamental thing. Algebra is formally thinking about expressions, right? So there are 100 problems of the time. Then we do not, I mean, we get into this problem, no, can our teachers do it? What teacher training do you have to do this? I know all these things, I've seen these discussions, but we can't be caught up in these. And by the way, I do want to remark on something that I heard yesterday. When presentations come, we immediately start asking, can we do this in all schools? Oh, can Chitra said something, can we do this in all schools? We cannot hold innovations hostage to doing in all schools. Huh? Right? God knows when the day will come. Some education secretary will come, some this thing will come. Maybe we can do it in all schools. Let's not worry about it today. Let's look for interesting ideas, powerful ideas. If I can do it, if I listen to something, I can take it and do it in my classroom. Let's be happy. So when somebody presents a paper and someone else asks, can we do it in all schools? What is the right answer for you? Make me education secretary. Right? They are not making education secretary. You are a researcher presenting ideas. Let's be content with that. As mathematics teachers, I think our this thing is to look for interesting ideas or ideas. Let the bureaucrats come and decide what will come right. There is enough problem and we need to battle that. But there are lots of things that we can do that we want to do. And if somebody gives us the opportunity, not always the case, when we get an opportunity, let's do it. That's the spirit I'm talking. Problem posing for making connections. Yeah. See, problems also help us. I think I already said about meeting the family time that we were. Okay. So, what are all linear functions fx equals a plus a greater than 0 have in common? Consider both the algebraic and graphical representations. Algebraically, if you start thinking about it, you say a times x plus 1. Okay. And not much fun. Immediately tells you that, okay, x equal to minus 1, this thing becomes 0, whatever value is. But the moment you think of it as in a geometric fashion, a is the slope, 1 is the y-intercept. Right? Okay, so you're talking about something with slope a and minus 1, 0. 0. That is the yeah. And then you're talking about the whole family of lines. Think about what they have in common. Think of representations. Very nice. Here's another one that I like. Show that whenever a plus b plus c equal to 1 and a minus b plus c equals minus 2, the quadratic equation a squared plus bx plus c equal to 0 has two different real roots. Now, real roots per a squared minus 4ac. If start formulas start coming into your head, this thing is going to take a forever. On the other hand, if I think of it as but what is this? Forget the equation. Consider the function f of x equals a squared plus bx plus c. The first one said, yeah, put x equal to 1. Right? X equal to 1. And the other one says put x equal to minus 1. F of 1 is 1. F of minus 1 is minus 2. You got two roots, two real roots. What's the problem? Answer is that. So it's again and again looking at algebraic expressions. Data. Right? Oblique. There is a lot to make. I should have look at Riemann parabola. I did it. Right. So the moment you think of that, it's again a parabola. See, now I'm talking about parabola, line physics thing. The same damn thing is different. Okay, this is something that I really don't have time for, but I love this parallel axis representation. We are only used the Cartesian XY orthogonal axis representation. This is something that Akashi and somebody else popularized in the 90s. And there's a whole cottage industry of mathematics that I've seen since then that people are doing. Parallel axis representations are I have one vertical line for x, one vertical line for y. Say put some 0, 0, minus 1, 1 above, 1, 2, 3, 4, 5, minus 1. Similarly, right? Now, if I want to point 1, 2, what do? point 1 here, point 2 there, draws a line segment. That's all. So every point on the Cartesian plane is represented by a line segment. Of course, if you want, you can extend the line. So this is a different representation of points in R2. But it turns out that, now you try to plot a function 2x plus 1 in this parallel axis. Okay. So it's a lot of fun. Try different ones and you find amazing things there. You start thinking about, okay, how is slope represented in this? This that thing, everything is parallel lines. How do you represent slope? It's about how tilted it is. That makes sense. How do I measure it? How does it work in this? Turns out that whatever function, linear function, I'm talking about linear functions that I represent here in the parallel axis representation, you keep finding one horizontal segment or some कुछ theta. Can I prove that it will always be, there will exist one and exactly one for all linear functions? Now, when I go, now this gives me a new observation. Oh, I see. These are particular linear functions. I can do this for every linear function. I can find something. There's one exception. Find all that. And then say, yeah, but you go to Cartesian plane and interpret it, reinterpret it. You've got two different interpretations and you can compare it. And then, of course, in the algebraic, the symbolic representation or the algebraic expression now looks different in different things. You can start correlating them. In fact, what is very nice is that you can prove that all these theta lines, actually, if you extend, there is a point at which they meet, which is called a focus. And so what is this relationship between the slope of the function, linear function, and the position of the focus, the relative x-axis? Okay, so beautiful explorations and investigations to be done. This is very simple stuff. This is higher secondary level, and you can do a lot. Of course, if you've got a tool, right, a digital tool out here, you can go really all over the place. Okay, so I don't want to do much of this. I just wanted to give something about, okay, what about logic? Problem posing for reasoning. Yeah. I mean, see, after all, what is it that we are doing? In all this, there's only one thing. You are trying to shift from asking what is the right answer to knowing why it is the right answer. Right? Not knowing the right answer, but explaining why. So reasoning is the matter. Okay, simple story. Three people go to a restaurant. One orders coffee, one asks for tea, and the third asks for buttermilk. Waiter comes with the orders. Asks who wanted coffee, gives it. Who wanted gives tea, gives it. Will she ask who wanted buttermilk? No, of course not. There are three people. Coffee, tea, buttermilk. Coffee, pucha. Tea, you don't ask. Can you show me? Okay. What about reasoning? What reasoning? I like that. Okay. So there are three logicians who go into a restaurant. And waiter comes and asks, does everyone want coffee? No. If you say you want coffee, you can say yes. Does everyone want coffee? They're looking at each other. First logician says, I don't know. Another says, I don't know either. Third logician says, yes, we all want coffee. What is the meaning here? Okay, the first one said, I don't know. What does this mean? That means she wants coffee. Why? Because if she didn't want coffee, the question was, does everyone want coffee? If I know that I don't want coffee, I just say no. Because I don't want coffee, that means the answer is no to the question. Is this clear? Externalization. Right? So she said no. Therefore, it's clear that she wanted coffee. She said, I don't know. First, the second logician has heard. The first one doesn't want coffee. What about this one? Again, if this person didn't want coffee, they said no. It said, I don't know. That means he must want coffee. So the third one knows that the first two both wanted coffee. And she wants coffee also. She says yes. So what are you doing here? You are doing reasoning about reasoning, right? Yeah, okay, not just saying that. I love it. That logic has full of problems like this, right? And this is about quantifiers that we are talking. The meaning of the universal quantifier. In logic, whenever you have a for all x statement, even one counter example means that the answer is no. Yes means positive answer to all instances. Right? That's all you are doing. This is also teaching. But there's a slight twist here from the previous problem, right? You're not only reasoning, but you're also reasoning about reasoning. There are lots of such problems. I just want to mention one beautiful problem from Martin Gardner. Martin Gardner, how many of you know the name? Lovely. Okay, the rest of half the people who don't know, please look up Google, find. We had the Martin Gardner Center years ago, and we had a Martin Gardner festival at the time. It was a pandemic, so it was all online. But yeah, he was a journalist writing for Scientific American, writing this column called Mathematical Miscellany. He's not a mathematician, but he just found lovely problems and puzzles to discuss. He was a problem poser, right? Many of them were not his own problems. He was just getting it from somewhere, but he would offer it as a twist. And often that is led to new mathematics as well. So this is a beautiful problem where he says, okay, I take two positive integers, x and y, distinct positive integers between 1 and 100. And there are two people, Mr. Sum and Mr. Product. And I tell Mr. Sum x plus y, and I tell Mr. Product the value x times y. So they both know I've done so, they can't hear. And the following conversation starts. Mr. Product says, I don't know what x and y are. Mr. Sum says, I knew that you didn't. Mr. Product responds, oh, now I know what x and y are. And Mr. Sum retorts, so do I. Find x and y. Okay. So this is reasoning about reasoning, right? To me, this is, and if you think some very fancy number theory is involved, nothing of that kind. Everything is high school stuff. In fact, not even high school, middle school stuff. But the reasoning is sophisticated. Right? Okay, what is the content of the first statement? This product says, I don't know what x and y are. For instance, suppose she had heard 35. Remember, I told her the product of x and y. If I told her 35, what are x and y? 5 and 7. Why? Because product of primes. So the first statement says at least one of them is composite. That is the information that you're reading. But then the second one is a really, really beautiful one. Right? I mean, I really think that you need logic. You need to know existential quantifier for all some quantifier relation. You write it as in fact, there's a good hint. Write it as a statement in quantified logic, you will be able to see the answer. It's not easy. So he says, this means what? Second statement is saying that the number I have got, no matter how I decompose it as a sum, x prime plus y prime, then what happens? At least one of them will be constant. I knew that you didn't. For all ways of decomposing this x plus y as x prime plus y prime, at least one of them is constant. Okay, so that is a but then that still leaves open certain possibilities. And the third one gives you the further information. This is another quantified statement. For all x prime y prime giving the same product x y, and for all x double prime but double prime additive decomposition of that, there exists at least one. Now you start doing all that, the numbers come down very fast. Then what is the content of the last statement? It says that it's unique. If it were not unique, it wouldn't be. So all these statements convey mathematical information, it's mathematical thinking. This is problem solving of a very high order. Very, very high order. Right? Okay. So this is like, oh, that Manade sound, right? Ha, 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 like that we say, right? It is of that kind. But you can still try to sing it, no? Maybe you don't get it like as beautifully as Manade did. But you can get the pleasure of trying to sing it. Right? That's what I'm trying to do. Okay, I don't want to go on. There are some other problems I want to mention. Let me skip all these. Problem posing for modeling. I wanted to mention some project, but I think Shobha did such a beautiful job of talking with let's speak like problem. Right? I think that's a classic problem for modeling. What better can you ask for? Right? I think it's beautiful. Right? So there can be many such. Easy. And let me end with saying that it need not be problems with all this thing. Good old abstract mathematical problems that can be quite alright as well. I Here is a problem I like very much. This is a seemingly structured problem. Consider 6 towns in flat land. The least distance between any two is smaller. The maximum distance between any two is bigger. Now show that bigger over small m is greater than or equal to square root of 3. I love this problem because it looks like they're just giving names. Right? You just name it little m and big M. There's no other information. From that you can find out. You look at it, it's really baffling. First thing you realize is what is the towns and flat land. It's the plane. 6 points for the plane. That's fine. हाँ √3 आ रहा है ना तो कुछ sin theta cos theta की बात नहीं कुछ है right so trigonometry I have to find the triangle there are 6 points I have to find a triangle I assure you it's great fun one about 1 hour but what is very nice is that I've done this problem many times and I think you can do this inequality but that leaves you with the question what particular configuration can I find a particular configuration of the points that actually achieves exactly equal to √3. This was very difficult. I could not do it. I have done it many, many times with children and teachers. Then one of my former PhD students, Ananta, who's a faculty in IIT of Madras now, he wrote a program. He wrote a program looking for polynomials. He found one that actually achieves. Okay. Here's a problem that these people who just walked in have heard about. So let me just put this in. Yeah. This is something that some Olympiad model session, some child pulled at me. Right? So he found it in some book, class 9. He says, sir, here's a problem. Okay, yeah, what is the problem? He says, show that 5555 to the 2222 to the 2222 to the 5555 is divisible by 7. Only children can ask me such a question. And it's horrible. So what is your reaction when somebody throws a problem at you? I don't know what is your reaction. Mine is panic. You know, panic in large letters. Okay, oh, there's no way I can do this. Right? But that's the point, right? Why can't we say it's normal? So we should tell our students, no, it's normal when somebody throws a problem at you and you can't do it and you panic. It's normal. It's what everybody feels. Feelings you don't give up, right? You stare at the problems, you keep staring at them, they keep staring at you and something happens, right? Something happens. And gray hair teaches you that you wait, थोड़ा patience, कुछ होता है, right? And that if we can somehow teach our children, right? Somehow we can teach our children that bit of patience. Don't give up yet. कुछ आएगा. आज नहीं तो कल होगा, right? That's somehow we want to give that assurance, right? Because you realize that okay, first thing you realize that 5 and 2 are a distraction, right? 5 and 2 are put there so that you're supposed to think about 7. 5, nobody is expecting you to work with these direct numbers. It's some a to the b plus b to the n, but a to the b plus b to the n क्या पता है कुछ नहीं. But a to the n plus b to the n, I can do some. Add something, subtract something. Remember when I said about handling expressions? If you are used to handling expressions, you realize that the standard trick that you do, add the same term, remove, make the exponents the same. Suddenly a to the n minus b to the n looks very familiar because it has a factor a minus b. Factor a minus b, I can make that 7. I tell you half an hour the whole thing also. It's like cryptograms. But these are very different kind of problem. Okay. So the main idea is that typically there is some looseness to the problem, necessitating discussion of what needs to be done, and it involves choices, you make some choices, you ask, what do you know? What do you need to know? And if you're using internet or whatever, which is okay, what's wrong? But access to information comes with the need to select. Check for reliability. You don't just call that. You can understand what's going on, see whether it is. So that kind of problem solving culture. So all the problems that I've been talking about, posing such problems come from very, very different areas, different books, different things. But that's exactly like if you can remember 100 film songs, and you do remember, you do remember 100 film songs, you can remember 100 problems, right? You can have it on your little notebook. Thing. We collect songs, we collect problems, whatever, collect stories, right? And we can do that. Okay, let me not go. So there's a whole lot of examples that I'm going to skip because time. Let me get to the end. Yeah. So formal problem solving gives a taste of doing math. Finally, that is that taste that I'm. So I think our goals could be very simple. And every batch, every year, can I make sure that every student has done one problem solving thing on his or her own, right? One genuine problem solving experience. Every batch, every student. You see that the moment you say every student, you already have, oh, my Mulligan is coming in front of me. I have to think about what will he use, what will I do, respond, right? Immediately you have. And okay, you have to make sure. That's the bottom line I'm saying. I'm not saying we do this all the time, right? Every class can I put up one problem, right? Keep posing, somebody will answer, right? That's it. But that taste is what I'm talking about. Changing our class. The other thing is that yesterday I think she mentioned in the slide. We say these things, but do we mean it? I don't know. The thing is, we should really genuinely believe in this. If we make our classrooms exploration centers, they actually offer far more space for children from all kinds of socio-economic backgrounds. In Azimut University, my class, there are students from Rajasthan, Tong, and Jharkhand in this. They're all first generation learners. Their parents have not been to school. They're sitting there. They enjoy this as much as somebody from Bishop Quarters in Bangalore was coming. Right? So it's the thing is that explorations equalize. Equalize very well. Content knowledge is different. Right? Access to technology is different. But exploration brings peace. So nurturing a culture of problem posing and solving can not only make mathematics education more engaging, it takes us closer to the central goal of mathematics education, which is to mathematics thought. So it's not about cleverness, it's about getting students to think, to talk, to try. I've not even touched on aspects like what is the kind of talk that happens in these classrooms. As I said, I'm not really talking about it from students' point of view at all. Simply today, I'm only talking about selection of problems, which problems for what pedagogical purpose. Already, I think there is a lot for us to think about. So let me enter this quote from Thurston, where he says, as teachers, we need to pay much more attention to communicating not just definitions, theorems, and proofs, but even more importantly, mathematical ways of thinking. We need to appreciate the value of different ways of thinking about the same structure. So Thurston's model is making the same point of Almos, but in a slightly different way. And I think what Almos is talking about, to me, that is the answer about why problem solving is the central thing of mathematics. In pedagogy, it teaches you different ways of mathematical thinking.
So do we have a feedback discussion?
Of course. Questions?
A lot of problems are raised from this side, so some problems will be raised from this side.
Yeah. I want to raise.
Yes.
Thank you, sir. Really, a very nice perception because as a teacher, I was thinking like Olympiad problem or JEE problem. These are the maximum which I could, given a thought on. But you have changed our perception. Thank you so much.
Still to me, problem posing and solving need to have a shared way to difference. If you could slightly more clarify between them. Yeah. So first thing is that okay, I can take this closer. See, without problem solving, there is no problem posing. So the whole thing is about problem solving. And to some extent, without experience in problem solving, you cannot pose problem. I didn't get to this, but part of that Sarasakya Abhiyan workshops that we did for teachers is to do problem solving with teachers. Because as mathematics teachers, often we never get the opportunity or the platform to sit together and solve problems. I hope you agree with me. And this is true at all levels, right? I mean, I may be a researcher, but it's if I go to conferences, it's only because you can sit together and discuss problems. That's the only reason, really, right? You listen to talk, but you actually sit and discuss problems. And you very rarely solve the problems when you discuss, but you get to hear, you get to think about it, right? Such platforms don't exist for us. So we need experience in problem solving because we are used to doing end of chapter exercises and going and offering end of chapter exercises. If mathematics problem solving is so important, we need that experience. Of course, the more experience you get in problem solving, a variety of problems you get exposed to. Same with Ghana. The more songs that you hear, even the one song that you sing, you can sing better, right? Somehow you have to hear lots of songs, right? Your ears have to be closed. This thing, you may sing only Kishore Kumar, but you must listen to Manade and Mukesh and everybody before you sing your Kishore Kumar song, right? Same thing. The more problems that you get exposed to, the more problems that you get immersed in, where solutions can be provided. It doesn't matter. Of course, it's much better if you don't see the solutions and solve it yourself, but it's okay. But if you get that experience, you can select problems. So here, what I'm talking about today was, once again, not creating your own problems. That's what I call problem composing. No, I'm talking about problem posing. I have got a lot of songs in my head. Which song for today, right? In my classroom, for these children with this pedagogic need, which problem do I pose? And how do I make sure that solving that problem creates that curiosity and interest or teaches what I intended to do? That's the purpose. Ruchi?
Thanks a lot for a very interesting set of problems that you have posed. So, I feel that there are two kinds of problem posing that might be happening in the classroom. One is problem posing in the sense of thinking about, from a set of very interesting problems, which one could do. And then the way the teacher contextualizes it
Yeah,
with respect to the classroom, with respect to each of those students, because when you mentioned that there might be certain students whose content knowledge might be at a different level from others, and for them you may have to again change it in certain ways so that they get that pleasure. So there are two levels that are happening.
I get it. So this is very important. And the thing is that that discussion is very important, but it's harder to get into without a bit of the education theory, this kind of background. There are so Jayashree and I, Ravi, Jayashree, we have worked on some of these things. We have tried to actually uh, develop some kind of desiderata for this, right? So we talk about, of course, you want the so-called low threshold, high ceiling problems, right? You want it in terms of choice of problems because you want something that everybody can try, get something, and a few can maybe. That's true, but that's not good enough. You need points, milestones, right? There are some things that you should be key points, key insights that you can offer. So there are milestones that you can reach, which gives you a sense of success. That's related to what you were just talking about, and you can do that. But that requires a lot more structure. No, no, lot more structure as well. Here, there is no structure. I'm just, you know, this is to create interest in that thing, but that's absolutely needed. And I personally feel that that's a problem in math education research. At least whatever I have seen, I don't see the problem posing literature having enough thing at all on this. I think a lot more research needs to be done, not only in the Indian context, I think per se. I wouldn't take the kind of classifications that Kai and that's there, and these are, to me, they seem superficial. It's not good enough to address the depth of this question because contextualization is very critical. So I'm not just selecting something and putting it in, like I talked about the handling algebraic expressions, right? There's a certain stage at which you can do it. Because to even do that reasoning, you should realize that, okay, when I see x squared minus 1 is a positive quantity I'm subtracting, what can it be? X squared plus 1 greater than 1. I need that reasoning, I need all that. And it doesn't come. It comes in a particular context in that. So I'm taking many things for granted that way. But a theory of problem posing requires a lot more structure. But Marianne Brown is, I think, one of the, I think her papers to me resonate best with me in this regard.
Yeah. So, just last question to you.
Thank you.
I've seen a lot of such workshops, training people on all these problems. But how many times have you seen teachers using in the actual classroom? I've never seen.
I'm one I use in my classroom. I started with
No, no,
it.
you.
I am a teacher. Let's not forget, I have been a teacher all my life. I have been a teacher all my life and I'll continue to be. And I have classrooms that I go to. So Monday morning, 8:30, I have to teach a class. So these compulsions are always there. So teachers do use in classrooms, but not just to make a joke of it. But the point is that I have seen many teachers. I mean, there is a very dear friend of mine, Mr. R Ramanujam of MTA. I've seen him do all kinds of problems with children, right? I've seen many, Shailesh's problem books, come on, right? So I've seen many, many. The point is that we do not have a culture of sharing these things, building resource base, doing more of these workshops or this thing. In my opinion, see, like I said, children love to show off, right? Students love to show off and come and say, and teachers also love to show off, right? If you've got 5 new interesting problems, what do you want to do? Go and share it with your children. That's what you all want to do. Everybody wants to do that. So the problem is that the humdrum routine, the routine, things have to be completed. There is a semester structure, there is a year structure, exams that take over our heads. I understand that very well. That's why I said our goal should be like through the year, everybody, one problem. Can we do that? My feeling is that if you start doing like that, it'll improve. But that's one.
I hope in the days to come, many more such teachers will go to classroom and will teach people like us. So thank you very much. Yeah.
Maybe we can informally interact with it.
Very pleased.
Thank you.
You want to announce some?
Yeah. Tea break.
One minute.
Thank you, sir. Please give a huge round of applause, everyone. Esteemed guests, we will now take a short break for tea and refreshments, which is provided near reception area. We encourage you to use this time to relax and network. Before this, please take a note that paper presentation session second is being organized after a break. Candidates, please assure to submit your essentials beforehand for smooth functioning. We will resume shortly, so kindly return to your seats by then. Thank you for your attention.
Just a minute, please. There's a poster presentation. Can you just see the time slot for that? Do we have poster presentation slots? 12:15.
12:15.
वो मैम उसके बाद होगा ना presentations के लिए बाद yeah stall to just make the announcement and act. Just one announcement. There is a there's a slot for 1 hour slot for poster presentation. Please do use that slot to go through all the posters and please interact with the presenters. So right after the paper presentation, the poster presentation will happen in the hall just here. And there are about 11 posters, so I think everyone should see them. Thank you very much.
Thank you, sir.
Thank you. Thank you, ma'am.